Up till now in this course, we've been talking about horizontally launched projectiles. That's a projectile that leaves a person's hand or a cliff or whatever it is. Whatever is going on, the projectile's velocity initially is all in the horizontal direction. So we would call that Vx. Say it's 10 meters per second. Maybe this is Wile E. Coyote that's running off a cliff, and in the real world, he'll take a path that looks like this to the ground. And in this case, the initial velocity in the y direction is always 0. There's none of this velocity that's directed downward. Okay? But now, with this video, I want to start talking about something different. This is a projectile that's not launched horizontally. It's actually launched at an angle. Maybe there's a cannon sitting on the ground. It's elevated at 30 degrees above the horizontal, and it's going to shoot a cannonball out at 100 meters per second. There's a couple similarities and differences with projectiles launched at angles compared to a projectile that's launched horizontally. Let's talk about the similarities first. The first similarity is that the x component of the motion and the y component of the motion are still completely separate and independent of each other. That's true for all projectiles. There is no way in the physics principles that exist in this world today, there's no way for x component of the motion and y component of the motion to influence each other. So whatever we start with here as far as the x direction, and this projectile does have a component of its motion in the x direction. If it didn't, it would go straight up and come straight back down. Whatever that component is, it's not going to affect the vertical component of the motion. And that was the same with a horizontal projectile. We proved that in a number of ways. One of those is watching the Mythbusters video where they shot a bullet and they dropped one from the same height, and we found out that those hit the ground at the same time. That proves to us that giving a bullet or any projectile tremendous horizontal velocity does not affect the vertical component of its motion whatsoever. We also proved that by shooting marbles out of the marble launcher at 2 different speeds. They also hit the ground at the same time. And it's going to be true with this as well. We're going to analyze the x component or the x component of the motion completely independent of the horizontal or vertical component of the motion. We'll still work them in the same way, where we'll draw the line down the middle of the paper and do x stuff on one side, y stuff on the other. So that's a similarity. Another similarity is the nature of the x and y component. With a horizontal velocity, the x component was always constant velocity. And the reason why we have constant velocity in the x direction for a horizontal projectile is because once Wile E. Coyote leaves the cliff, there's no other forces in the x direction that act to change his velocity. As long as we neglect air resistance, which we do in this class, there are no forces to change the velocity. And the same is true here. We're still going to neglect air resistance with these problems. So x velocity is still going to be constant. Still going to have no acceleration in the x direction. And similarly, in the y direction, we are going to have acceleration just like we did with the horizontal problems. And for the same reason. We still have gravity working. Just because a projectile is launched at an angle doesn't mean that gravity all of a sudden doesn't exist anymore. We still have gravity working, and we're still on this planet, so gravity is still going to be negative 9.8 meters per second squared all the time. I don't care whether the projectile is here, 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 or here. The acceleration in the y direction at any of these points is a constant negative 9.8 meters per second. That acceleration will cause a decrease or increase in the speed of the projectile in the y direction, depending on what we're talking about. Some differences, 2 differences I want to discuss between angular projectiles and projectiles launched horizontally. Number 1 is this. We will usually divide these down the middle because we in effect have 2 trips. We have a trip up and we have a trip down. That was not the case with a horizontal projectile. There was just 1 trip. Really, with a horizontally launched projectile, all we had was the trip down. Now we're going to incorporate all of this. Okay, and we're going to start from the very beginning. So we're going to have 2 components of the motion to look at, and these dynamics are actually very interesting as far as comparing one side to the other. We're going to be talking about symmetrical motion again. Another difference between horizontal and angularly launched projectiles is this. With a horizontal projectile, whatever speed it came off the cliff at, that speed was all directed in the x direction, and we would call that Vx. With these projectiles, the speed that they give us, for instance, 100 meters per second, and this problem would be worded in such a way, it would start out by saying, a cannonball is launched from a cannon at 100 meters per second, elevated at a 30-degree angle above the horizontal. So this is the velocity we get. But this velocity is about an object that is not moving in an x or a y direction. It's moving in both directions at the same time, kind of like the Etch-a-Sketch thing. We're doing both handles at the same time. In physics, we cannot work motion problems or force problems if the direction is not in the x direction or the y direction. In other words, this component, or not component, this velocity we cannot use because it's between the x and the y directions. The first thing we have to do with this, and with every single projectiles at angles problem, is we have to resolve this into x and y components. And you already know how to do that. We already know how to resolve a component. There's the x component of the velocity, there's the y component. And we already know that to get the y component, I'm going to do v sine theta. We know that shortcut already. This is the v, 100, times the sine of the angle. So to get this y component, I would do 100 times the sine of 30. And to get the x component, the shortcut to get that, in this class at least, is always going to be v cosine theta. So I would enter the v I'm given, 100, times cosine of my angle, which is 30 degrees. These two things will get me the x and the y component. The y component then becomes my initial velocity in the y direction for the trip up. On the way up, this is my initial velocity in the y direction. And this becomes my velocity in the x direction. This is the x velocity that is constant through the entire trip. Which means, once we get these two, this one is gone. We cannot use this number anymore. It's not useful to us because it is not in an x or y direction. This is the initial velocity in the y direction on the way up. And if we can treat the y direction as only the y direction, in other words, straight up and down, what this is in effect is just throwing something up and then it comes back down. With a horizontally launched projectile, we started here and we came down the back half. In other words, with a horizontally launched projectile, all the y component of the motion was a simple free fall problem, where we have an object and it's falling. The initial velocity up there was 0. We also know if this one is moving upward, it'll eventually come to a stop at the top because of gravity. And that gives us a final velocity of 0. These two happen at the same instant. Again, we've already done this before. In the y direction, all this is a free fall problem. We have an object that's being thrown up and then coming back down. And at the same time this is going on, we have this constant x motion that's happening at the same time. And we put the two on top of each other and we get this trajectory. You'll see more about what that means when we work some more of the problem.